me tell you how a scientist tells a statement. I am a student, you are a student, and you brought a sample to me, and I'm sitting in my office, and you tell me, sir, is my sample crystallized or not? Right? So I'm not in a position to tell you the correct answer, because I don't know what is your sample, how much you have treated it, was the furnace properly calibrated or not, was the initial ingredient you used pure or not, were they 99% pure, were they 99.99% pure, I don't know. But when I look into the sample, and you had brought me that the barium titanate sample, and heating that material at 1000 degrees centigrade turns its color a little bit yellowish or greenish or translucent, say, or transparent, then from that I can tell you that you have treated this material at this temperature, and maybe there is this phase, maybe. Right? So when I used to take my samples to the greatest glass scientists of the world, I was fortunate to have that opportunity. And when I took my sample to that professor and asked him that, sir, can you tell me that is my material amorphous or crystalline? The first reaction was, who am I to tell you whether your sample is amorphous or crystalline? Then I told him that, sir, my professor says that ask him, because he is the best professor, the most experienced professor of glass technology in the world. He said, okay, when your supervisor says, then let me go. And he came with me from M floor to the C floor and looked into an instrument which is called glass weaver for 5-10 minutes in every direction. And his statement was that according to the resolution of this instrument and the resolution of these 60 or 80 years old eyes, I couldn't see any stresses in this glass. I said, sir, my supervisor is not believing in you couldn't see. His question is, are there any stresses or not? His answer was that if you could find a younger person with a better vision and a higher resolution equipment, maybe you will see some. This is the standard of the expert statement. We don't know ABC of things and swear upon God that yes, this is. So this is the difference between a literate and illiterate person. So never argue on things about which you are not 100% sure. And everything in this world is relative. This wall is solid because it is at the room temperature. You heat this wall at 1300 and it will be liquid. So its existence, its presence is relative because of this temperature and this pressure. I am a living person because of the temperature range available on Earth and the environment I have, the atmosphere. If I don't have this environment and not a little bit higher temperature, I will be no more here. So as a scientist, think logically. Don't believe things blindly. And there is always a logic behind everything in this world. If you have mixed barium carbonate with titanium oxide and you got barium titanate and there is no account, there is no reason, there is no explanation for the remaining material, you are not a scientist. You must know that when barium carbonate reacts with titanium oxide, carbon dioxide will be evolved and you will be left with barium titanate. If you had mixed 20 grams of sample and you got 15 grams of the final material and you couldn't explain where the 5 grams went, you are not a scientist. You must have a logic and you must explain things according to the proper logic. Okay, when it didn't happen after 90 hours, I left it for 120 hours and I found a little bit crystallization in the sample. Then I heated it for 331 hours. And then I found another phase there. Then I heated it at 408 hours. Then I found another phase there. And then I heated it for 551 hours. Then I found two phases here. So, what does this mean? That when you start from a specific temperature and go high, start from a constant temperature and increase the length of heat treatment, you are giving opportunity for crystallization of various phases. But do you remember what was my scanning speed for this? If your material is 100% crystallized, or you say, for example, there is 50% crystallinity, a 1 hour or 2 hour run of the X-ray diffraction is okay. It will tell you about the crystalline phases. But if your material has 5% crystallinity or 95% is some other phase and 5% is some other phase, then you will have to go very slowly. If all of you have the same faces and the same bodies, then only looking like this is enough. But if every one of you is different, then I will have to look into every face very carefully so that I recognize each one of you. The more I stay my eyes on the specific face, the more explanation I will get from that face. Similarly, if something is smaller there, then I need further care in comparison to the others. So the same thing is in the techniques. If you are just interested in quick phase analysis of the material, quick phase analysis is enough. 1 hour XRD, 1 degree per minute is enough. 2 degree per minute is enough. But if you are interested in very small proportions of phases, then you will have to scan the X-ray very, very slowly. And the very, very slow means you give enough time to every feature for the X-ray to be diffracted from, right? So that is why some people do slow scanning, some people do, and I myself did 0.1 degree per minute. And it used to take 15-16 hours for the one sample to run. So in science, there is no holiday. In science, there is no holiday. Whether it is Eid, whether it is Ramzan, when you are doing an experiment, you must be 100% concentrated on that experiment. And for that reason, I am not a good scientist or a good teacher or whatever you say, but my house was always in the middle of the university. And even in the Sehri time, I used to run to change my sample in the department. I didn't care about iftar and Sehri, but I took care of my sample. In the evening, I am studying a sample, and I am working on this from the morning. And if I took it out or switch off the machine, I will have to work for another 12 hours upon it. So I am looking into this, right? So this is the true scientific nature of a person. That when you are looking into something, then you must look. Nobody will do this, but a mad person will do it. And what I used to do, 1, 2, 3, 4, 5. I put 5 samples in the furnace. After 90 hours, I took one out and shut the furnace abruptly. After 120 hours, I took another sample and shut the door. So at the same time, I ran all the 5 samples for more than a month, and I studied the whole phase transformation sequence When I took the sample out, what I did, first of all, I polished it and etched it. Etching. Remind me at the end, I'll tell you about etching, right? So I etched the sample, polished the sample, smoothen the surface, make it shiny, so there are no scratches because of the polishing on the sample. When there is no scratch on the sample, then you will be able to see the final rearrangement of atoms, the orientation of planes, the crystal morphologies inside the material. Then you will be able to do it. I looked in the optical microscope, I couldn't see any crystals. If you can't see any crystal in the optical microscope, this never means there is no crystallinity inside the sample. Go to a high resolution instrument, because the crystal can be macroscopic. The crystal can be macroscopic, M-A-C-R-O. The crystal can be of microscopic dimensions, micron, several micron, submicron, and the crystal can be at nanoscale. The dimension will be of nanoscale. So you can't see nanoscale things on the optical microscope. So I look into it in the optical microscope. If I saw something, well and good. If I didn't see, then I go to the scanning electron microscope. Then I go to a transmission electron microscope to see the complete microstructural evolution in the sample I have made. This was the visual thing. X-ray give me the phase analysis. Scanning electron microscopy, wait, X-ray give me the phases formed inside the material. Number one, whether it is amorphous, whether it is crystalline. It also told me what is the crystallite size. The crystals are big or the crystals are small. How? I'm giving you a very common sense like argument. If the crystal size is large, no. If the material is crystalline, the peak is sharp. When the material is crystalline, the peak is sharp. When the material is not crystalline, it is a hump, amorphous hump. Now, when there is long range order, the peak is sharp. When there is short range order and completely no long range order, it is a hump, right? When the crystal is large, the peak is sharp. When the crystal is small, then the peak will be in between. So, for nanomaterials, your XRD plot, instead of if this is the broader this area, the smaller the crystal size. The broader the full width of the half maximum of the X-ray diffraction peak, the smaller will be the crystal. So, decrease the size of the crystal and it will broaden. And get rid of the long range order, it will become a hump. So, if your material is nanocrystalline and the peaks are like this, as I told you, nobody will believe that you are telling the truth. Because nanomaterials should have peaks like this. They should be broad. So from here, you knew about the crystallite size. Now when you decide the technique, then go from here. DTA brought you to XRD. XRD sends you towards microscopy. Right? So, the peaks due to large crystals, big crystals will be sharp. The peaks due to small crystal will be broad. Now, how much broad is broad and how much sharp is sharp? How much sharp is sharp and how much broad is broad? Because if you run the sample from say 10 degrees 2 theta to 20 degrees, then a sharp peak will appear broad. And if you go from 10 to 80 degrees, then a broad peak will squeeze down. So when you treat sample, take a standard and check your sample data in the previous literature that at which 2 theta angles the major peaks of the sample occur. A careful scientist will start from 10 degrees to 120 degrees to see the whole spectrum. But once you know that your material is crystallizing, the reflections of the phase forming in your material are mostly covered from 10 degree to 70 degree, then it is a reasonable level. And here you can compare where the peaks are sharp, where the peaks are broad. And secondly, as a scientist, little more, these are not scientific terms. How much more is more? How much far is far? How much small is small? You must be quantitative. If you say small, then how much small is small? Because small can be 1 mile, small can be 1 meter, small can be 1 inch, small can be 1 centimeter, small can be 1 millimeter, small can be 1 angstrom. Right? So as a scientist, always be quantitative. So if I could see the crystals in optical microscope, well and good, and I will say these crystals form. XRD told me that which phase it is. Now, orientation of the crystal. If a crystal is like this, and how do I know which phase is which phase? If I do transmission electron microscopy of this sample, it will give me a diffraction pattern. After diffraction pattern tells me this is 100, this means this is the A-axis of the crystal. After diffraction pattern tells me that this is the 010 direction, then this is the B-axis of the sample. So if this is the A-axis of the crystal and this is the B-axis of the crystal, the direction through which I am looking into it, it is the C-axis of the sample. Secondly, the transmission electron microscopy has the capability to tilt the sample. But the better the resolution, the better the quality of machine, the less will be the freedom of rotating the sample. Because the more precision comes in the smaller area, you always pay for benefits. So if you want higher resolution, then you will have a little bit less freedom. If you don't care about the resolution, then you have a great freedom in the choices. So there are some machines which have very good level of freedom. There are some machines which are very strict, restricted to specific angles. So if this crystal was in this direction and you found another crystal which appeared like this, for example, this means that I was seeing this face of the sample and the other face is this. So don't get worried if you see different features within the sample, because you are looking into this phase. So when you look into this phase, you think the material is something elongated crystal, but when you see this, you say the material dimension, the crystal dimensions are not that much elongated. But when you go look into this phase, it becomes plain. So never decide the morphology of your crystal on the basis of the one image you see. Look into the sample throughout Take the diffraction patterns from the crystals. The one diffraction pattern will give you looking through C phase, the other will give you looking through A phase, the third will give you looking through B phase, and in this way you will make a three-dimensional visualization or picture of your crystals. People join things. People join the diffraction pattern. People join the various phases of it, and they sketch it to explain to the examiner, to the reviewer, to the public that how the crystal look like in the electron diffraction pattern. In scanning electron microscopy, you can see crystals, but it is usually for the grain morphology, the grain boundaries, and this type of thing. Scanning electron microscope has no diffraction facilities in it, right? So you started from the peaklet of DTA. XRD told you which phase is forming there and told you about the approximate size of the crystallite inside the material. Then, to look into further into the material, you went to scanning electron microscope. Then from scanning, you moved toward the transmission electron microscope. But look into your needs, how much you need to do, and decide on the basis of that. Because if you are doing DTA, you spend, for example, 1,000 rupees. When you went to XRD, you spent another 1,000. When you went to the optical microscope, you spent another 500. When you went to scanning electron microscope, you spent 5,000 rupees. When you went to the transmission electron microscope, your image cost, if you are taking 10 or 50 images, it costs you 100,000 rupees. Is it worth to do it? Is it needed for that study? If you are interested in microscopic size crystal, optical microscopy is enough. That this is the crystal morphology, this is the phase. But if you are interested in very, very fine details of the sample, for example, you are interested in the electrical properties of the sample, then you need to study the structure up to nano level, because the nano domains will reorient easily in comparison to the macro size domains or polarization of ions or crystals, right? So it depends upon your need. Which technique do you need? Not that when you see an electrician and your home electricity gets broken. When you see a doctor and pain appears in your head, no, not for that purpose. Check logically, ethically, scientifically, that do you need a specific technique? If no, don't bother about it. If yes, then do it with full concentration, with every care. For example, you were making a material and it was left on this table when it was raw material in the start, and you are making different products or materials or phases or crystal from that for the 3, 4, 5 years of your PhD, and your material is contaminated, then you wasted your 5 years time, your 4 years time, and wasted the resources which could be used for some positive work. So a scientist must not be working blindly. He must be smart and vigilant and must know his priorities. What is his job? Most of the students I see, when they do a project, they don't know why are they doing it. If it is for the piece of paper, then find some easy thing, do it, and find a corrupt teacher and he will give you a degree within a couple of years. But if you are really a humane human being and you are not wasting your own life and the resources, then you must know why are you doing this project. And when you have in mind the why, that why will take you through all the steps very carefully. But when you can't answer the why, then in my opinion, you are wasting your time. The next thing,
get any difference between the study of nanomaterial and transmission? And how can we identify with our
Nanomaterial is this, the broader peak, and the bulk, the microscale crystal will give you sharp peaks. The nano peaks, you should give longer time so that the intensity may not be that high, and in some cases the peaks may not be very resolvable. For example, you see a peak like this, right? But here I see a little bit edge. So for a common man, for an inexperienced person, it is a single peak. But if I broaden it, then it is like this. But when it was squeezed, it was appearing like this. So when I opened it up, then it was corresponding to, say, 111, and the interclaimant spacing was, say, 4.30 angstrom, and this corresponded to 4.33 or something like this. Now, why this splitting occurs? If the crystal phase is more symmetric, if the crystal phase is more symmetric, smaller number of parameters, lattice parameters, will be enough to describe it. What is the most symmetric shape in the world? The most symmetric shape, sphere, or square, or cube. These are the most symmetric. Only one parameter is enough. What is the radius of the sphere? And you knew about the whole sphere. But if this sphere, a little bit, now I need two parameters, right? If it becomes like this, then I will need more parameters. Same thing is here. If a crystal structure is cubic, like this, A is enough to describe it. Because when I say cubic, this means ABC angles, alpha, beta, gamma angles are 90s. And A is the latest parameter, this is enough. So, there will be smaller number of peaks here. Because XRD is giving me the parameters to describe the crystal nucleus. If I a little bit elongate it and the C-axis was longer, then I need A and C both. A is equal to B, not equal to C. So I will need more peaks. Right? So if double phase start to appear in a material, it was originally this peak. But if second phase formation started, then here another peaklet started to appear. So this shows me the transformation of the cubic structure into the tetragonal structure, because the nearest is tetragonal, for example, if it is energy-wise feasible, right? So if this appeared after, say, 90 hours, after 180 hours, the peak appeared like this, and this finished. The material completely transformed into tetragonal phase. When I heated it further, another dot appeared here. And when I deconvoluted it, these were two peaks, not one. This means some other symmetry is forming here. So always be careful. A little bit shouldering or a little bit change in edge of the peak gives you a lot of information about the phases forming there. Similarly, if two phases are forming very close and the DGF naught has given you a peak here, but this peak is not symmetric. This means if you deconvolute this peak, you will get two peaks from here, and they may be two close temperatures of phase transformation. And do you know what occurs when phase transition occurs? It completely changes the behavior of the sample. A material which changes its phase, its crystal symmetry, changes its lattice parameter. When the lattice parameter changes, the volume of the cell changes. When the volume of the cell changes, the material expands. When the material expands, then the phase transition, which was caused by the application of electric field, and it expanded, it pressed something. That pressing something makes the material piezoelectric. And all the sensors in the world, most of them are working on the basis of that. You just change the symmetry at a particular temperature or a particular field. You change the symmetry. You polarized and unpolarized the material. You give and take energy. And the whole technology is based on these things. So slight variation in phases. If a tetragonal phase transforms to cubic and it releases energy, that energy can be used for work. So the phase transition temperature is very, very important to know about the material, because by changing the phase electrically through electric field, you are making the material to do work. If little energy or less energy is needed to do something, the material becomes, the process becomes less expensive energy-wise. And that is why people are moving towards nanoscience and technology. Because when the crystal domains are at the nanoscales, it is easy to reorient them. Because you are playing with the surface of the material. If the material is in the bulk, then you need a lot of force or energy to do what you want to do, right? So, I did this, XRD told me this, then I analyzed the XRD data and I characterized the phases. That what are the latest parameters, what are the symmetries, and I knew the full story of material phase analysis.